But it's much more straightforward to, rather than using a formal basis, use the standard basis of FPN. And so if we do that, we can construct a new semifield. Let's say you've got A and KS. We construct a semifield out of FPN with standard vector addition, and this multiplication star A, which is the multiplication defined by A on that basis, on the standard basis. And if we do this, the resulting semifield is going to be isomorphic to our semifield S, and our multiplicative identity will be E1. And so by doing that, we then look at this subgroup of GLNP, which I call CNP, which is going to be the set of all matrices in GLNP whose first row is E1.
So actually GLNP is invertible n by n matrices with entries in FP?
Yes.
Okay. I don't recall seeing that in your thesis defined there, so I might have missed it.
It's in the automorphism part.
It was in your, okay. So I went very quickly through the first half and focused on the second half.
Okay.
Standard.
Yeah.
That is standard. GLNP, that is standard. It should be defined in the thesis, but it is standard.
Oh, you mean I didn't define GLNP? Yeah, I thought that was standard enough.
Well, I had to guess what it was because it started with GL, but see, n parentheses, n comma p would mean n by p matrices. Right,
yeah.
So now, an n by p matrix cannot be invertible though if n is equal p. So I was looking at it thinking, you say at first, and I was like, okay, I think it means n by m and n should be p. So
okay,
if you have not defined it in the thesis, I
it should be
recommend
defined in the thesis, but in Lie groups that is standard.
Is that standard?
Yeah.
in groups?
Yeah, I mean in finite, in GLNP.
And I'm not used to working with
Finite fields, right, yeah.
But I do recommend, if I missed it, then
No, that's
then
fine.
okay.
No,
But if
I did not.
it's not there, I do recommend.
No, I defined CNP, and that's what I thought.
Yeah, I think
but
I
did
saw
not.
that.
But I did not define
We
GLNP.
showed that.
Let's move.
Yeah, sorry. Yeah. Let's move on. Sorry. But yeah, I will correct that. So the reason I bothered defining CNP though is it's going to serve two purposes. So any basis of FNP whose first entry is E1 is going to correspond to a matrix in CNP where the rows are the elements of that basis, right? So every basis is going to be contained in CNP in a matrix form, and furthermore, any two such bases where E1 is the first element, the change of basis between those two is also going to be in CNP. And so what this allows us to do is we can then say that there is a group action of CNP on the set KS. So for any A and KS, for any F in CNP, using the triple product FF, F inverse transpose times A is going to give us some other cubical array in KS. And by Knuth's theorem, there's a linear transformation F corresponding to that matrix, such that if B is equal to FFF inverse transpose times A, and we use star A star B to define multiplication by A and B on the standard basis, then they're going to be related by this function. So they basically are going to be an isomorphism in the case where all three of those are equal. So the question comes in, when is this going to be an automorphism? And when this is going to be an automorphism is if your multiplication on the left side and the right side are both equal, and that's going to happen if and only if your cubical arrays A and B are equal, which gives us our result. So if you've got A in KS and F in CNP, and you let B equal FF inverse transpose times A, then the linear transformation F corresponding to that matrix F is going to be an automorphism if and only if A is equal to B. So this allows us to find all the automorphisms of S by just picking an A and finding all of the matrices that will, through this triple product, map A back to itself. The problem is CNP is kind of large. So just using some linear algebra, you can show that the size of CNP is equal to the product from I equals 1 to n minus 1 of p to the n minus p to the I. But this does give us a way of discussing the size of KS now. So the size of KS is equal to the size of CNP divided by the size of the automorphism group of S. So if you guys don't mind, we can go through an example. looking back at system V, it had multiplication defined in this way, and it gets this cubical array with respect to the basis 1 omega lambda lambda omega. So if we wanted to determine the automorphisms of V, of system V, what we would do is test all of the matrices in C42 and see which of those with the triple product map A back to itself. So C42 has 1,344 matrices in it. So obviously you would have a computer do this. I had Mathematica do it, and it returned these 6 matrices. So these 6 matrices will map our cubical array back to itself. And if we wanted to view system V as just the vector space Fpn with the multiplication defined by that cubical array, then these would actually correspond directly to our automorphisms. But since we had an algebraic definition for system V, we can actually get an algebraic representation for those automorphisms. If you'll notice, the first matrix there is the identity matrix. So I'm not going to talk about that because it's trivial. It's going to be the identity automorphism. So let's look at the second matrix. And I'm going to let phi2 denote the automorphism defined by this matrix. So the rows of this matrix are where your basis elements are getting mapped to by the automorphism in vector form. So the first row tells us that the first basis element is getting mapped to itself. The second row tells us the second basis element is getting mapped to itself. The third row tells us that phi2 of lambda is equal to lambda omega. And then the last row tells us that phi2 of lambda omega is equal to lambda times 1 plus omega, which is equal to lambda omega squared. So from that, you can tell that this is what phi2 of a plus lambda b is going to equal to. It's going to equal a plus lambda b omega. And from that, you can determine all of the automorphisms of S in a similar way. Now, let's say you had a larger semifield where CNP was not so small. CNP, like I said, can get quite large, so you might want to save some time, even with the computer. And we can use the properties of automorphisms to help us do that. So if A is an S and phi is an odd S, then phi is going to preserve our left exponential powers and the right exponential powers. But I only really care about the left ones for now. So basically, phi of a to the ith power is equal to the ith power of phi a. And the corollary to this, though, is that if you have a in S and phi in odd S, then the left minimal polynomial of A is going to be the same as the left minimal polynomial for phi of A. If A is left primitive, phi of A will be left primitive. If A generates a left cyclic basis, so does phi of A. So, in the case where you have some element that will define a left cyclic basis, whether it's primitive or whether it just defines the basis, you only have to check p to the n minus p matrices rather than that product of p to the n minus p to the I. So, and to prove this, basically the argument is, let's say you've got that cyclic basis, and you use that to generate your cubical array. Then any other cubical array that's going to be it, basically, since your automorphism is going to have to map it to itself, any other basis that generates that cubical array is also going to have to be a left cyclic basis. And if you look at the vector forms of your elements with respect to the basis you used to generate A, the change of basis matrix from A to itself is also going to still have to be, its rows are going to have to be the left powers of some other element of S. So basically, you're going to have to look at matrices, what do I call it, F? Yeah, matrices Fi, where Fi star, that's the ith row of F, is equal to the vector form of the I minus first left power of B for some B in S, and since B can't be a scalar, there's p to the n minus p possibilities. So that dramatically reduces the number of matrices you would have to test. And finally, we can conclude by talking about extending subfields of semifields. So, going back to the definition of a semifield in Knuth's theorem. So he said we can construct a semifield over a formal basis if we have Knuth cube. So the active construction over a formal basis will satisfy the first two axioms of a semifield. the third axiom, the lack of zero divisors, corresponds to the requirement that the Knuth cube be non-singular. And then the existence of the multiplicative identity corresponds to the fact that the Knuth cube is in standard form. So the question is, when could a cubical array A, which defines a semifield over Fp, when could that define a semifield over some extension of Fp? So let's say we've got a cubical array A, it's n by n over Fq, just some finite field. We'll let bracket A, so Pm, denote the n by n cubical array over Fpm, where the entries of bracket A sub Pm are the entries of A under the natural embedding into Fpm. So basically, if A is in standard form, bracket A Pm is going to be in standard form as well. So the necessary and sufficient condition to satisfy for A to define a semifield over Fpm is that bracket A Pm has to be non-singular over Fpm. But if you guys remember, the definition of non-singular is kind of tricky, right? It's got to be it's got to yield a non-singular matrix for all non-zero vectors in our vector space. So we'll talk about that in a little bit. So first, I want to introduce one more notation. So let's say you've got a semifield S, and you've got some cubical array A and S, A and K of S. We'll use S sub bracket M to denote the algebra constructed by using bracket A Pm to define multiplication on the standard basis of Fpm Pn. So that might not be a semifield because it might still have zero divisors, but it gives us an easy way of just talking about this act of extension. And I actually call S sub bracket M the M inflation of S, because essentially what you're doing is, since you're extending a subfield, you've got this like existing semifield around that. So when you extend it, you inflate your semifield. So the question is, when will this actually yield a semifield? Oh. Well, before we get to that, I guess, let's talk about what this preserves. So the nice thing about this inflation is that it will preserve your isotopism relationship. So if S and S prime are isotopic semifields, and if the M inflation of S is a semifield, it's going to be a semifield if and only if the M inflation of S prime is a semifield. And if they are both semifields, then they're also going to be isotopic. And this is another nice thing about isotopism. If you prove it for isotopism, the fact that it works for isomorphism just follows directly, just by using a special case of the isotopism. So isomorphic semifields that inflate will yield isomorphic semifields. All right, now for the question of how can we determine whether or not this M inflation actually gives us a semifield. So one way to do it would be to turn this problem into a problem involving polynomials. So we define this, what I call the inflation polynomial of A, to be this polynomial F, where you take the sum over the indeterminates x sub I with the slices A, I star star, and then that'll give you a matrix. You take the determinant of that matrix, you're going to get a homogeneous polynomial in n unknowns of degree n. And the M inflation of S is going to be a semifield if and only if the inflation polynomial has no non-trivial zeros in that extension field Fpm to the n. And so looking at system V and system W, the nice thing about this inflation polynomial is using those cubical arrays for system V and system W that I showed way back at the beginning. If you take their inflation polynomials, you get the same polynomial. So system V and system W are going to both either inflate or not, depending on whether or not this polynomial has roots in whichever extension field you're looking at. So there's no easy way of solving this thing. So basically I just, again, used a computer, had it test every possibility, and by that I was able to see that this thing had no non-trivial roots in F8 to the fourth, F32, right, and F128. So so both system V and system W have 3, 5, and 7 inflations.
I'm just reminding myself, these are just no non-trivial zeros. We don't need left zeros or right zeros.
No, this is just a normal polynomial.
Over a normal finite field.
Yes. And that's the other nice thing about cubical arrays, is everything in them lives in a finite field, right? And so when we do that, when we create this inflation polynomial, this is all in a finite field.
Did you use Mathematica or Magnet?
I use Mathematica. And actually, I think for this, I used GAP, because Mathematica had a hard time dealing with polynomials with this many variables, all from a finite field. All right, so I still do not have a good answer for when inflation is going to be possible, but I've found some conditions for when it's not possible. So basically, if the M inflation of S is not a semi-field because it has zero divisors, and M divides R, then the R inflation of S will not be a semi-field because it will also have zero divisors. A similar case arises if the characteristic polynomial of LA for any A and S has a root in FPM, then the M inflation will have zero divisors. Or if the left minimal polynomial of any A and S has a root in FPM, then the M inflation will not be a semi-field. And so this is my conjecture about this. I'm still not sure how I'm going to prove this, but it seems to me that, let's say you've got a semi-field S with Q to the n elements, where Q is the largest field over which you can view S as a vector space. Then the M inflation of S will be a semi-field if and only if M and N are relatively prime. So that's probably the case, but I still have to work on that. And then so some future ideas in addition to that. Going back to polynomials, I feel like there's probably some relationship between the set of left minimal polynomials and the set of right minimal polynomials for a semifield and the actual structure of that semifield. So maybe we can use...
Of the same semifield?
Yeah, of the same semifield. I'm thinking maybe if you define maybe the left minimal polynomials for elements and then define the right minimal polynomials, could you use that to construct a semifield? I think that might be possible. Or maybe once you've got your left minimal polynomials, can you use that to construct the right? I'm not sure. But this was an idea that I think there might be something there, so I'm going to look into that. Something else I thought of when I was preparing for this was I've got a pretty solid idea of how to compute the automorphisms of S. So if I can compute, if S of M, if the M inflation of S is a semifield, I should be able to compute the automorphisms for SM using the automorphisms of S, and probably the automorphisms of whatever that extension field is. And finally, I still need to figure out a good way of determining when inflation is possible. And two other conjectures. Again, this is stuff we already mentioned, but I'm pretty sure that every semifield has a left cyclic basis, and I'm pretty sure every semifield is going to be isotopic to a semifield with a left primitive element. I think these can be proven using cubical arrays. I just haven't been able to do it yet.
That's pretty strong. The second conjecture is pretty strong as well.
I actually think it'll be easier to prove than the first, though. And that's because of...
But I thought you said there were semifields that did not have
Yes.
left primitive.
Right, up to isomorphism. So this is the distinction, right? So I want to study semifields up to isomorphism. If you stop at isotopism, you can have isotopic semifields with just very different algebraic properties, right? The most stunning for me is the fact that you can have a commutative semifield isotopic to a non-commutative semifield. So I've been trying to study them up to isomorphism, and in my thesis I really look at the 16 element semifields in detail.
Why is isotopic? You remember that was the very beginning of your talk. Why is isotopic even?
Oh, because isotopic semifields coordinatize isomorphic projective planes.
So is there a property of having a left primitive element that shows up in the associated projective plane?
I don't know. I don't think so, but there might be. I'm not sure. Because normally when people look at the geometry of these things, they're specifically looking at just properties of the plane. Not so much of the elements of the semifield, but maybe the general way you can define the product of the semifield. So yeah, I don't know if that's been looked at, but I'm thinking I can do it just using cubical arrays.
That would be a product. To my geometric mind,
yeah,
obviously, that would be an obvious thing to look for if you're at all looking at the geometry of the projected planes, because isotopic semifields should have isomorphic.
Yeah.
So somehow the left primitive element should somehow be a cycle.
Yeah.
A cycle, a path.
It should, right? It should be obvious somehow.
Yeah, a path that, I would think a path that covers the entire plane or something.
So actually, this is something that Lillian is working now with Big Jam on working on those left primitive elements and plus the geometry.
Oh, okay, so you don't want to scoop her, I guess.
Yeah.
Okay.
Well, and again, I'm trying to.
Well, there, yeah.
But I mean that they can't be.
Yeah.
I mean, if it's
yeah.
yeah.
I mean, also, I mean, if this was not like doable or feasible, then motivating this study from the point of view of connecting it with geometry would actually be redundant.
Yeah.
Right. There probably needs to be more hidden connections going on to make that relationship be worthwhile. And so one place to start would be looking at primitive elements and seeing how that is reflected in the geometry of the plane.
And again, I'm trying to stay away from geometry. I just like I like these cubical arrays, and I think I can do this just using cubical arrays. But yeah, so if Lindley can do it using geometry, then I just got references. So
all right,
that is it.
Are there any questions from the audience?
We start speaking.
Just repeat everything. No? Well, then I will dismiss the audience and thank you for being here.
Thank you. And then we'll sit out and wait for Kelly. You can go that way, Mom. Okay, I can do it.
I think I should remove the recording device as well.
Yeah. I don't know how practical.